Okay, in this video we're going to look at the SN1 reaction, the second type of substitution mechanism that we'll see in organic chemistry. We previously looked at the SN2 reaction, and we'll see that the things that favor the SN2 reaction are virtually the opposite to those that are favored in an SN1 reaction. To begin with, let's look at the rate law for an SN1 reaction. When we talked about SN2, we said that the rate is dependent on the concentration of the substrate and the nucleophile. Now you'll notice for the SN1 reaction here, the nucleophile is nowhere to be found. In other words, the rate is dependent only on the concentration of the substrate. So if you were to increase the concentration of your nucleophile, it wouldn't affect the rate at all. That implies then that the slower step in the reaction involves just the substrate. And that's exactly what is observed in an SN1 reaction. It consists of two steps. Every SN1 reaction does. And the first step is always spontaneous loss of the leaving group. Now, because this is only breaking of a bond and no bonds are formed, this is an energetically unfavorable step, and hence it's slow. The first step is always slow in the SN1 reaction. When we break that bond, we form a carbocation intermediate. This carbon here is sp3 hybridized. This carbon here is sp2 because there's only 3 groups around that carbon, so I've lost the stereochemistry there. And there's a carbocation now. There's a positive charge on this carbon. And the main reason why particular substrates favor the SN1 reaction is because of the stability of the intermediate carbocation. This carbocation here is secondary, and the more stable the carbocation you can form, the faster that first step's going to be. So tertiary carbocations are the most stable, followed by secondary, followed by primary. And primary carbocations are not stable really to any degree, so you won't see an SN1 reaction with a primary alkyl halide. So this is the first step in any SN1 reaction. Okay? So far we've seen that the reaction is 2 steps, and this is the first step. The second step is what happens with the nucleophile. Now notice we have this water nucleophile here. We classify this nucleophile as weak because it has no charge. The SN1 reaction is favored by weak nucleophiles. Okay? If you imagine we have 2 competing effects here, the leaving group coming off and the nucleophile coming in. In an SN2 reaction, the nucleophile is strong enough to come in at the same time as when the leaving group leaves. But if this is a weak nucleophile that only goes in really slowly, if at all, the leaving group is going to come off first. So the SN1 reaction is always favored by weak nucleophiles, such as water here. So when we draw in what happens between these two, the lone pair from the oxygen and the water will go to the carbon with the plus charge, the carbon that's lacking electron density. Now we're going to go back to an sp3 hybridized carbon when we draw out our product here. So we do have to think about stereochemistry. If you remember in the SN2 reaction we saw inversion of stereochemistry where R went to S and S went to R. When we look at the SN1 reaction, it's a little bit more complicated. Imagine that this molecule is flat, or at least the carbon here is flat. This is an sp2 hybridized carbon. If you remember the geometry of an sp2 hybridized system, that is trigonal planar. So this is flat, meaning the water can add from one side or from the other. And because it's completely flat, there's no preference to adding in either direction, which means that it actually adds in both. Now that doesn't mean it adds in 2 places at the same time. What it means is we get 2 different products. We get one product in which the water adds from the front, and I'll draw this product out here, and then we get the other product which is essentially exactly the same thing except where the water has added from the back, because there is no preference to add one way or the other. If you were to look at the stereochemistry of these two products, you'd see these are actually enantiomers of each other, and they are existing in a 50-50 mixture. Alright, they're present in a 1-to-1 ratio because there's no preference to form one over the other. Because these are present in a 1-to-1 ratio, there's equal amounts of each. This is called a racemic mixture. Alright, a 1-to-1 mixture of opposite enantiomers. Now what this means for the overall stereochemistry, this is where we get something called scrambling of stereochemistry. And what that means is when we look at the initial stereochemistry here, this is S, we go to something that's S here and R here. So we've gone from one stereocenter to kind of a mixture of two. That's what this scrambling means. So in an SN1 reaction, we're always going to get out two products that are enantiomers of each other. So the two steps here, the first one is always slow, the second one is always fast. Now these are not the actual products because this was a weak nucleophile. We have a proton transfer reaction that happens at the end where the extra proton is removed from here, and so we end up with one alcohol that looks like this, and then the other alcohol that's the enantiomer of the one I just drew, which looks like this. Okay, two enantiomeric products. So the SN1, the SN2 reaction always forms one product, the SN1 reaction always forms two enantiomeric products. So we talked about the number of steps, we talked about the rate law, we talked about favored by tertiary alkyl halides because of the stability of the carbocation. We talked about the stereochemistry, we talked about how they're favored by weak nucleophiles, and the only other thing that we need to consider is the solvent issue. SN2 reactions are favored by something called polar aprotic solvents, and because everything seems to be the opposite in the SN1 reaction, then that's the same here too. SN1 reactions are favored by polar protic solvents. Now the most common solvents that you're going to see that would be classified as polar protic would be water or alcohols, and the simple reason for that is that the hydrogen bonding available to these two is able to stabilize the carbocation and the anion that forms as well, because here we have the Br minus, okay, and in fact that stabilization from the solvent is the main reason why this carbocation forms in the first place. Okay, the hydrogen bonding present in these solvents allows for stabilization of the carbocation, which is not the case for polar aprotic solvents. Okay, that's why polar protic solvents favor SN1. So those are the basic details of the SN1 reaction. Two steps followed by a proton transfer. The first step is always slow, second step is always fast. Scrambling of stereochemistry, and that is the SN2 reaction. I'm sorry, that is the SN1 reaction.